Osmari Aponte, and today I'm gonna talk you about my PhD research entitled Automated Analysis of Ground Deformation Time Series. Geoenergy activities such as gas production, geothermal energy, and CO2 storage are expanding worldwide. These technologies are essential for the energy transition, but they also require reliable monitoring of ground deformation. Ground deformation is a key indicator of subsurface processes, and scalable automated monitoring is becoming essential. Satellite remote sensing supports this by providing cost-effective, wide area, long-term observations, and even the possibility of establishing historical baselines for comparison. Today, deformation monitoring mainly relies on two complementary techniques, GNSS and InSAR, which I will briefly introduce. Despite their strengths, current approaches face a key limitation. We cannot simultaneously obtain dense spatial coverage and full three-dimensional deformation information. GNSS stands for Global Navigation Satellite Systems and use ground stations that receive signals from navigation satellites orbiting the Earth. This allows us to retrieve high accuracy positions on 3D with temporal high resolution. In this example, we use daily solutions. However, these precise measurements are only available at sparse station locations. Interferometric synthetic aperture radar, or InSAR, uses radar satellites that repeatedly observe the same area. What InSAR really measures is the projection of the ground motion onto the satellite line of sight. That is the direction connecting the satellite and the target on the ground. This geometry is defined by different angles. To obtain deformation time series, techniques such as persistent scatter interferometry analyze many images of the same area and identify stable reflectors, like buildings or exposed rocks, that repeatedly return a consistent signal. After processing these observations, we retrieve non-deformation time series at numerous ground points. In this work, we integrate GNSS and InSAR time series within a non-uncertainty-aware framework. GNSS observations are projected into the satellite line of sight, and both datasets are combined using a weight least square strategy. This allows us to reconstruct a consistent three-dimensional surface deformation field. The resulting 3D deformation products are interpretable, reproducible, and suitable for automated monitoring. Here is a simplified view of the results, where the blue represents the GNSS, orange the InSAR, and the green corresponds to the integration method. By integrating GNSS and InSAR, we move towards scalable and operational three-dimensional deformation monitoring, supporting safer and more sustainable geoenergy applications. This research was made possible by the European Union's Horizon Europe program and the Marie Slowacka-Curie Actions SMILE. Thank you for watching, and stay tuned for more updates.